All right, I think we're here. We've got a couple of things today. We're going to come back to our strain gauge. I've added this to it, so I just soldered on wires that actually can plug into breadboards or prototyping boards, just so that the wires that were here before, they were braided or stranded rather. They weren't really braided. They were stranded wires, and they, they're too flimsy to plug into the board. So I soldered on some pins that can plug in, so that we can do that. We need to build the bridge circuit for this. We're not going to build the amplifier circuit today, but we're going to build the bridge circuit. It's going to consist of some of these parts over here. We'll get to that in a minute. We're going to look at this little switch. It's a Mercury switch. At least I assume it's Mercury inside there. It's a really simple switch. It's not really digital at all, although I guess it is on and off, so in a way it's digital, but it's not electronic. It doesn't have a processor on it or anything. We'll look at that. We're going to look at uncertainty. So how do we begin to calculate the uncertainty that goes with any measurements that we're making? You've always seen this number, this nominal value, plus or minus some other number. We're going to figure out how, or at least start to figure out how to do that plus or minus part. I think where we should start, well, how don't we start with the bridge circuit? That's interesting. So the idea here is we've got a strain gauge mounted to our aluminum beam, and mine is still stuck on there. It's pretty good. Sometimes you'll see these have been coated with a potting compound to kind of keep them, for one, not affected by humidity and temperature, or at least not as much, and also to keep them stuck down. I didn't do that, and you probably won't either. It's probably just going to look like this. And so the idea was that we could flex the beam here one way or the other, put the top of the beam and hence the strain gauge in tension or compression. And when we stretch out the strain gauge, remember it had all those little wires inside there, and those wires would get stretched out and their diameter would change, get smaller, and their resistance would get higher. And the opposite would happen if we put it in compression. And so these wires, this red, white and black wire coming off of here, they're attached to the strain gauge, and I can use them to measure the resistance. Hopefully it's still working. I haven't checked it recently. Let's see. This ideally was a 120 ohm resistor strain gauge. Let's see. It still is, so that's good. It's 120.4. And hopefully it's still, yes, resistance goes up when we put it in tension, and it goes down when we put it in compression. But that's resistance, and most of the time you're not going to be able to measure resistance directly, unless you have a multimeter or something like that. But we want to use our Arduino to measure this resistance, and it can't really do that. But it can measure voltages. So we need to put this strain gauge into a circuit that will let us, kind of like we did with the thermistor and the photoresistor, where they were in a voltage divider circuit and we could measure a voltage based on their changing resistance. We're going to do a similar thing, but not just a voltage divider. This one's going to be called a bridge, a Wheatstone bridge. And it looks kind of like this if we were to draw it out. A lot of times you'll see it drawn out and it's actually a diamond shape. And I'll draw that one first because that is what you normally see as far as whenever you're showing a picture of a Wheatstone bridge. So we have a voltage source. So for the Arduino, that voltage source is either going to be 5 volts or 3.3 volts. We'll probably use the 5 volts. And then the bridge is over here. We're going to have a static resistor. We have another static resistor. We're going to have our strain gauge right here. So I'll draw it with this arrow on it saying that its resistance can change. And then another static resistor here. So really, this is just 2 sets of resistors that are in parallel with each other. One of the resistors is a strain gauge. Later on, we're going to change one of these resistors to be a potentiometer, this guy. or one like this. I don't know, it doesn't have to be this one. So this one, let's see if I can even see it. I think it's a 200 ohm maximum. Let's see. We need to talk about how these things work. We're still connected to our strain gauge. So this guy has a maximum of, 205 ohms. Our strain gauge had a nominal value of 120 ohms. These three resistors right here that I've picked out, they have a nominal value of 120 ohms. I haven't actually measured them yet to see what their actual value is, but it's somewhere around 120 ohms. And so we can adjust this. The potentiometer, the idea is that it's a variable resistor that I can change its resistance. Not quite the same way that I changed the resistance on the strain gauge, but if we get close enough to this, there we go, getting back in the picture. It has this little, and most of them have something like this. Sometimes it's just a knob, a knob on an amplifier or whatever. That would be connected to a potentiometer on the other side. But here, I've got this tiny little screw. You can actually see the R200 on there that's showing that it's a 200 ohm resistor, at least maximum 200 ohms. I can turn this screw, and what happens inside here is, let's see if we can draw what's going on inside here. So I don't know exactly how it's built. I didn't take it apart, but there are three, whoops, we're out of the screen. There we go. There's three legs coming off of this guy, and the outer two are basically connected to a resistive element of some sort. Again, we're out of the screen. There we go. Gonna have to zoom out. All right. A resistive element. So this leg and this leg would be the outer ones. So if you measure across the outer ones, you're going to get the maximum resistance. And then you've got this middle leg that it is in the middle, but it's not set, or well, the leg is set, it doesn't move around. But this screw in here turns a wiper that this wiper can move back and forth. And I'm kind of simplifying what's actually going on inside here with the mechanics. I don't even know if I could get this open. It looks like it's yeah, I don't think it's going to come open where we could actually see what's inside this one. It looks like it's plastic welded shut. So I don't think that's going to happen. But anyway, turning this screw will cause this wiper to move back and forth. And it's touching the resistive element. And so what will happen is if I measure across these two, I get this resistance. If I measure across these two, then I get this resistance, so a smaller amount. There's less material to pass electrons through, so it's a smaller resistance. Here, there's more material that the electrons have to pass through, so it's more resistive. If you, let's take a for instance. I don't know where it's set right now. It could be set at one end, or I don't know. We'll see. So remember, we measured across the whole thing, and it was 200 something, 204 or 5. 205 ohms across the whole thing. So if I measure from the red side here to the center, I'm at 205 ohms. So that means I'm almost all the way at one end. So if I measure the other side, I'm going to have, 0.5 ohms. And I can adjust it by turning this screw. And it gets larger and larger. So I'm moving that wiper, and eventually I actually want this to be set somewhere around 120 ohms. So let's go ahead and set it there. Let's see. So something we don't know exactly where yet, but somewhere in that range. And so what I did by turning the screw is I moved this wiper more to the center. It was basically set all the way at one end, so that pretty much I had the 205 ohm resistance across these two pins, and basically 0.5 ohms it said across these two. All right, so we'll come back to that. We don't need it quite yet. We will need it later. as one of these resistors. I don't know which one exactly we'll set it as. There's several options. A couple of things you can do is you could make this parallel to the entire circuit, kind of to help balance things out. What we're probably going to do is just replace one of these resistors with this potentiometer so that we can balance the circuit. We don't even know what that means yet, so don't worry about it. But there's several options for where we can put this. All right, so this is the Wheatstone bridge. So Wheatstone bridge. There's our potentiometer. Well, not our potentiometer. It is our strain gauge. One of these other resistors we'll just replace with our potentiometer. Probably the one over here. It doesn't. We just want to be able to balance the circuit. What we do with this is we're going to measure voltage across here. So this will be V. I don't know what we call it. V out maybe. This would be V in. Although it's not the actual V in that's labeled on the Arduino, it'll be the 5 volts that's labeled on the Arduino, not V in. So we'll measure voltage across here. And so let's think through what's going to happen. So let's make an assumption that's not true, but it will give us an easy number to work with. Let's say that we have 1 ohm, just so we have easy numbers. 1 ohm, 1 ohm, and this guy is set to 1 ohm nominally, so when there's no strain. So, and we could use any number as long as they're all the same number. So we could use 120 since ours are all around 120 ohms. So if I did that, then what I would have is I have 2 loops here, right? Voltage loops. So if I start here, I can go down this path and get back to where I started, or I can start here and go this path and come back to where I started. So there's 2 loops in there. And Kirchhoff's voltage law says that the voltage in a loop adds to 0. So I've got 5 volts here. So I've got to have a 5 volt drop across these 2. And I also have to have a 5 volt drop across these 2 because they're, this loop, this closed loop, we need to have plus 5, minus 5. And same thing on the inner loop there. So if I have 5 volt drop across these 2 resistors, they're the same value. That means both of them have a drop of 2.5 volts. So there'd be 2.5 volts here, 2.5 volts here. And that same thing would be over here. If I have 5 volts coming in, I have to drop 2.5 here, 2.5 here, and it's equal. It's both 2.5 because these are equal resistance. So I'd have a 2.5 volt drop across this resistor and a 2.5 volt drop across this resistor. And when I try to measure this voltage, I'm trying to measure the relative voltage between this point and this point. It's 0 because they're the same. There's no, one of these is not larger than the other one. But when I change this resistor, I flex the beam and it changes its resistance. Now I have new numbers. Let's put them in red so that I've changed it. These didn't change. These were just static resistors. This one didn't change. They didn't change their resistance. So this is still 1 ohm. This is still 1 ohm. This is a static resistor. It's not going to change its resistance much at all. At least not because I stretched this one out anyway. It might change its resistance if it heated up or something like that. But we're assuming that's not happening to us. Although these guys, remember this one? These guys have lots of problems with changes, even in humidity, temperature. There's all sorts of things when you get into actually trying to implement a sensor like this, or any of the others. The thermistor or any kind of sensor in the real world is going to be affected by environmental conditions. So you have to account for those somehow. They'll even, if you think about this one, if it has a weight that's sitting on, there's a little tray that goes up here. If it has a weight that sits on it for a long period of time, then it will eventually begin to creep. The metal itself will begin to creep, and that will induce strain in your strain gauge, and then your measure that this thing weighs a different amount than it started. And that's generally not true. most things stay the same weight unless they evaporate or something like that. And so you do have to account for these things. In fact, if you have a little digital scale, most of them turn off after a while. You leave them on. Some of that's to save the battery, if it's a battery powered scale. Some of that's to save the battery. But even the ones that you plug in, a lot of times they will turn off after a minute or 2 minutes or something like that of continuous operation. If you just leave them sitting there and the weights just not being removed, a lot of them will shut down and turn off because at some point they are going to begin to drift, is what the term would be, from the value that they originally recorded for the weight of this object or whatever. So there are all kinds of environmental things that you do have to worry about. Right now we're assuming that they're not affecting our ideal circuit here. Let's say that our potentiometer did change its resistance. So it went from 1 ohm to 2 ohms. So it's more resistive. So it was in tension. We flexed the beam and it put the strain gauge in tension. So it's got more resistance. Now that this has more resistance, this value and this value are no longer true. These two are still the same. They still have their closed loop here, 5 volts in, 2.5 here, 2.5 drop here to get back to 0, and they haven't changed. But the relative voltage here have changed. They still add to 5, but this one's not 2.5 and this one's not 2.5 because these resistances are not the same anymore. It's 2 to 1 now. So we could figure out, let's see, if we know Ohm's law, V equals IR, we have a total resistance in this loop of 3 ohms, right? 2 plus 1 is 3. So if we have 5 divided by 3, that gives the current going through here. We'll draw it this way. Current is going to equal 1.67 amps. Another reason you don't really want these little tiny resistors, 1 ohm and everything, because you don't want nearly 2 amps going through your circuit. But that's the numbers we chose. So if there's 1.67 amps going through a 2 ohm resistor, that is 3.3 volts. And the same current would need to go through this one. The Kirchhoff's current law basically says that resistors in series have the same current in them, and these two resistors are in series. So if I have a 1 ohm resistor with 1.67 amps, that would be 1.7, I'm rounding here, 67 to 7 volts. So now they don't have the same voltage anymore. This 3.3 plus 1.7 still adds to 5, so my Kirchhoff's voltage law, 5 volts in, minus 3.3, minus 1.7 gets me back to 0. That's still true. But now when I measure the voltage across these points, I have the voltage across this, from here to ground is 2.5 volts, and from here to ground is 1.7. So there is a potential across these 2 points now of 2.5 minus 1.7, 0.8 volts across here from this point to ground and this point to ground. I've got a 0.8 volt difference. And so that I can measure. And this voltage change is directly related to the fact that this strain gauge changed. Why we need, I've already lost it, here it is. Why we need our potentiometer is that we're not going to find exactly the right resistors. In fact, let's measure what we have. Let's see. If we can find, I have 3 that are supposed to be 120. So these are brown, red, brown, and then a gold band, so they're 5% tolerance. Let's see if I have any that are in the same ballpark as one another, and they should be around 120. Brown, black, or brown, red, brown would be 120. So let's see what we've got. This one is 118.8. So let's keep track of these guys. This one's 118.8 ohms. So close to 120. This one, 118.1. Okay. our strain gauge nominally was, what was it? 120.5? Yeah, or 0.4. Again, depending on how it's doing over there. 120.4 for the strain gauge. There are different ways to spell gauge. I've been spelling it G-A-G-E, but sometimes you'll see it spelled with a U, and they're both correct as far as I'm concerned. 119 for this one. All right, so, well, we had that one. Here it goes. All right, so this one's 119. So, of what I have available, this is ohms, it looks like the 118.8 and the 119 are the closest to each other. This guy is the furthest out of tolerance compared to the others. So we're going to get rid of this one. I want to go with these two. We can set this one to balance out. So if we put, you know, maybe the two here that are roughly the same. They were 118.8 and 119, so that's pretty close. And if I set this guy to balance the strain gauge, so I set it to 120.5, which we can do now. Let's see, I don't remember which leads were set up for that. All right, so that one's close, 121. If I use the middle and the one underneath the screw, see if we can get it to 120.5. All right, that's probably good enough. And we can put it in here. Then our circuit will start out balanced. So it'll start out where it's not exactly like 2.5 volts and 2.5 volts, but it's close. If we had a big stack of resistors, we could go through and sort out each one of these to be exactly 120 ohms if we went through enough of them. Or we could just put 3 of these guys, you know, one in each spot, and set them all to exactly 120.5. But we're going to build it with this. All right, so I'm going to get the 5 volts from the Arduino, so that's what these are doing. And then that 5 volts is going to need to come over. I can use this little guy. And it's going to need to come into the positive side, and I'm just going to put it right here. So that's bringing 5 volts from Arduino over to this row, and that row needs to go to our strain gauge. So strain gauge doesn't matter which end of it, so we'll just put it here. And the other end needs to go to the one part of our potentiometer, so we'll put it right here, trying to get it lined up with all the little holes. I missed one. All right, I think it landed in where it's supposed to go. Now we want to measure. Let's put over on this side. We need some little probes to measure with. Let's see. I think I had some. Oh yeah. We'll use this. It's just 2 male ends on a kind of long set of wires. It doesn't really matter. I just need something to plug in to here and plug into the Arduino. So I need to measure across here. So we'll measure one end is there, the other end is there. So these purple and blue are what I can use to measure the voltage across here. And here I've got coming off of where I plugged in either the purple or blue, in this case the blue, to ground. So I'll put it here, and I can't really reach all the way to ground. I'm going to make a ground row over there. All right, did it go in? I think so. And this guy is going to go from the point that I measured the purple, which is kind of the row underneath here. It's all kind of crowded up on my breadboard. And it goes to the same ground, and then now I need to ground that row, which I can use this one. Ground is this blue line. Well, it will be when I plug it in. Let's see if I can get it. All right, so that should be our bridge if we've plugged it in right. Now I need to power it with 5 volts, so I need to get the Arduino over here close enough to do something with it. Okay, I've already got 5 volts coming here, so let's just use that one. I guess I could have built it on this circuit or this board. I just didn't. I'll probably move it over there later on. It's not particularly great that I have the resistors here sticking way up in the air. These legs are kind of acting like antenna. So once I start wanting to measure with Arduino, then I might get a lot of interference on that. So I'm going to have to cut these and get them down to where those legs aren't sticking up like that. But for now, we're just trying to get it to work. Need to power the Arduino. Okay, so now I should have 5 volts going into my circuit, and I should be more or less balanced, right? The strain gauge is at 120.5, potentiometer is at 120.5. These two are really close to the same value, so I should be more or less at 0 volts. Let's switch over to DC volts. Now remember, this is an auto-ranging multimeter, so I don't have to pick what range of voltage. If you have a multimeter that does, then you're going to expect a really low voltage here, so put it on the smallest range to start with. All right, let's see. Wait, I've got 2.5 volts. Uh-oh. Well, that's a lot. Why do I have 2.5? All right, let's see if I have made a mistake in my... Oh, did I put the guy backwards? I don't think so. Those are going to ground. This guy's going... Look at my circuit diagram. Going between here and... Oh. Right. This one's not connected. There we go. I had the... when I built this part, I had the... this is the black wire here is part of the strain gauge, and I had it in the row above these, so they were not connected at all. All right, so now I've got a really small voltage, which is what I was expecting to get. All right, and hey, look at that. The voltage goes up, but it goes from 0.001 volts to, you know, I think we could go maybe 6 or 7. At most, we could get to 0.01 volts before I think this aluminum bar would bend permanently, and we don't want to do that. And it should go down also. Yes, we do get the negative swing, which if it's not, I don't ever plan to use this in the negative direction where the top's in compression, but it does work if we do that. The problem that we're at now is that this is a very tiny voltage, and our Arduino is not going to read that very well. So we need to make this voltage larger. So we can make it larger by, you know, straining the strain gauge, but we need to amplify it. So we'll do that next time once you get to do this. So you should be able to connect your strain gauge to your Wheatstone bridge, put your potentiometer in there. I used it to balance the strain gauge, so I basically set it to the same nominal resistance as the strain gauge. It can really replace any resistor in here, but there are some that are better than others. This spot is where I would put it, unless you have just problems with that for some reason. I would put it as the one that's opposite or mirror image of the strain gauge, and it does work. So it's working. It's just a really tiny voltage that next time, or soon, I don't know if it'll be exactly next time. I think it will be, but it depends on how I go about this. We need to amplify this so that the Arduino can actually make sense of it. Right now, it all probably looks like 0 volts to the Arduino, even when we strain it. If I were to try to do an analog read, it would probably basically always read the same value, because I can't get enough difference from unstrained to about as strained as I think I want to put this beam. You know, there's probably not enough actual voltage difference that the Arduino could actually pick that up. So we need to multiply this voltage coming out of here, and we'll do that with the operational amplifier next time. All right, so get yours to do that level. This strain gauge can be one of the sensors that you do for your big project. If you want it, you can do the thermistor. You can get your own sensor. We did the photoresistor. I'm going to go ahead and unplug this, get it out of the way, and let's look at this guy real quick, and then we'll do a bunch of circuit stuff. Not circuits, uncertainty stuff. We're doing circuits right now. All right, let's get this out. This is, you don't have this in your kit. It's just something that not everything has to be complicated. So this is a switch, and you might have used something similar in a accelerometer to measure tilt. This one doesn't really measure tilt, but it measures if something has been tilted enough one way or the other. It's basically on and off, but you can see there's a little ball of metal sliding around in this glass tube. I don't know if you can see. Let's see if I put it down, if we can zoom in close enough to see what's inside there. I don't know if we can or not. Maybe you can see that. But what's inside are this is a longer piece of metal inside this tube, and then there's a shorter piece of metal inside the tube, and then you've got, you know, the glass thing around it, and then inside there, when it's sealed up at the bottom too, inside there is this metal bead of, I think it's mercury. I don't know if this particular one is mercury or not, but they used to be mercury. In fact, they were called mercury switches. And as this tilts, that ball of metal can either make contact between the longer and shorter leads, or it can roll out this way and only be touching the longer one and not making contact here. And so what you get is, if we hook this guy up, let's hook him up to the sound. So if we measure in this particular one, it's these outer, this one also has a LED and all kind of other, well, a little resistor on there. We're just going to measure it as a switch. So when it's tilted down, it's not, there's no continuity. And then, so it can be a very simple tilt switch. It doesn't give you anything about the amount of tilt, other than it's more or less than whatever degree you mount it at. You know, maybe it's horizontal and then up to, I don't know, maybe 10 or 5 or 10 degrees, and it is going to tilt and come on. It's not a lot. This one's pretty sensitive. It really is only 5, maybe 10 degrees tilt causes it to go off. So you can use it as a simple tilt detector. It's not a digital device at all. It's not going to give you how much did it tilt like an accelerometer would, but it will give you, did something tilt over or not. So it's a cool little thing. Mercury switch, tilt switch. This is kind of, there's a whole package of these pre-packaged little sensors on Amazon. I don't know the name. I'll have to look up the name of it, but it's got like, I don't know, 50 different sensors, simple sensors. Some of them are digital. You know, they have circuitry along them. Some of them are analog like this, where it's just a mechanical device or something like a mechanical device that completes a circuit. I'll see if I can find the list of it. It's kind of a handy thing to have, and they're kind of pre-packaged and set up so you can plug them into a breadboard and test them out to see if you would want a thing like that in your actual design. All right. Uncertainty. So this is leading us into why we've been looking at some of the statistics and things like that. How we've been, the normal distribution and even the T-student distribution, why we've been doing some of that. So let's see if I can get my notes here and see where I put them. Here we go. All right. Let's talk about experimental uncertainty. And it does, whoa, we're still zoomed in, aren't we? There we go. Experimental uncertainty. So, and it's not necessarily just experimental uncertainty. It could be, this is an active system. It's not a research type thing. It's just the uncertainty associated with the measurements that you're taking. So these uncertainties might come from the equipment themselves. Maybe your multimeter has a certain tolerance on it that it is not going to give you any more accurate than plus or minus 0.1% of the nominal reading, or who knows. I don't know how to find that. We'd have to find the data sheet for this particular one to know what that tolerance is. And so there are ways that you can find the tolerances, the uncertainty of a particular measuring tool. It could be that the thing you're measuring just changes over time. It gets hot and there's some random change. The humidity might affect it. Moisture might affect it. I guess that's kind of like humidity, but I meant being submerged. Temperature certainly can affect these things. Corrosion could affect it over time, although that wouldn't necessarily be random. Some of these would be more, they are systematic. So if it got corroded, then it's going to consistently give you a wrong measurement. But there might be some randomness too, and so a lot of times you have to figure out, am I dealing with a random error or a systematic error? Some of the error could be, I have this analog device and I am hooking it into a digital device, and that digital device has to approximate the analog signal. And we've talked about the A to D conversion. We talked about it a little bit. We haven't really gone into how that works yet. We'll do that later. But that conversion from an analog continuous signal over to a digital representation of that signal, there's going to be some approximations, and that could be error. So you've got all these different errors. We talked about systematic, and we talked about random. Sometimes the systematic, in what we're going to do now, the systematic error So that's where your scale is just off by a pound every time you use it, or your calipers aren't zeroed and they're off by 0.02 millimeters every time, or whatever it is. Sometimes this will be in the equations that we're going to do now, B or beta, and they're using a B here for bias. So there's something that's consistently biased against the measurement, like the calipers are not calibrated, or your scale is just off all the time. And then there's random. These are more, you don't get the same offset every time. A lot of times these will be P in our equations. So B and P will be bias or systematic error, and P will be random error. You can kind of think of P because there's a probability associated with the random error, so that P you can think of as from the probability. We've also talked about a little bit in the T distribution. If you remember, the top row of that had this significance level of significance. We haven't done a lot with T distribution yet, but there was this level of significance. And if you remember our graph, our normal distribution graph, for the T distribution, it looked something like this, and there was this shaded in little area, one of these tails, and it was called, actually that was called alpha over 2. So the total would be, if we shaded in the other side too, that would be the other alpha over 2. And alpha was this level of significance. What this is similar to is a confidence interval or a confidence level. And a lot of times alpha is going to equal 95%. Sometimes alpha will be the 99.7%. You might see this occasionally when you're dealing with measurements and uncertainties in measurements. You might see, instead of 95 and 99.7, this is more the statistical way of talking about it. You might see it presented as odds. And so 95 would be 20 to 1. and 99.7 would be, I think it's 340 to 1. So you'll see sometimes these two, 20 to 1 or 34 to 1 or 340 to 1 after a measurement. So maybe you have, I don't know, voltage equals 5 volts plus or minus 0.1 volt, and then you might see 20 to 1. What that means is that your 95%, 20 to 1 relates to 95%. If you did 1 divided by 20, you'd get the 0.05. And so you're 95% sure that this interval is correct. Maybe you see it written as 5 volts plus or minus 0.15 volts, and that is at 340 to 1. So I've increased the tolerance, and now I'm more certain that this is the correct tolerance that goes along with this measurement. So sometimes you'll see these odds. It's kind of like you're making a bet. That I'm willing to bet 20 to 1 that this is correct, is kind of what it's the analogous to. So one thing about what we're about to do with the uncertainty is that all of our uncertainty, so if I'm using a multimeter and ammeter, a separate tool, and some other tool to measure all these things that I'm converging together into one equation to calculate some measurement, all of those measurements need to be made at the same, and it's usually 95% or 20 to 1. They need to all be made at the same confidence interval or the same confidence level. I don't really, like, the equations aren't going to work later on. I guess they'll still work. You can still do the math, but they won't mean the same. If I do some measurements at a 95% confidence interval, and then I do some of my other measurements, maybe I measured the current at a 99.7% confidence interval. So they need to all be at the same confidence level. You don't always get to control that as far as your tools. You may not know the confidence interval for 340 to 1. Maybe you only know it for 20 to 1 for one tool, and you know it for another tool. So you might have to manipulate those. These are just statistical numbers, so you could, if you know one of them, you could figure out the other one. Ideally, what you do is you make so many measurements that you create this yourself. You create your own normal distribution and figure out what the nominal value is. That's usually not going to happen unless this is what you do. But if you're just taking your multimeter out and you need to measure a resistor to put in a Wheatstone bridge, you're not going to measure 1,000 resistors to figure out what your confidence interval for your multimeter is on that type of measurement. You're not going to do that typically, unless it's the thing that you do. So normally we're going to be operating at this 95% uncertainty, well, certainty, I guess, 5% uncertainty range. But each tool is going to have its own tolerance, its own plus or minus on the end, uncertainty associated with it. You might think that we have systematic error and random error, and some of the error we can calculate and figure out what it is, and some of the random error we can do some statistics and figure out what those are and just add the two together. And you can do that. What that'll do is that'll give you the worst case scenario. So it'll give you the largest possible value that you have as an uncertainty, which may be useful. If that's useful for getting started. So maybe you want to do a measurement. Maybe you're building a bridge circuit like we just built. It won't move over here. There it is. You're just building this, and it's on a breadboard, and you just want to get something that is in the right ballpark to start with. Maybe that makes sense to find the worst possible scenario. But typically, you're not going to simultaneously get the worst case systematic error and the worst case random error in one measurement. You're typically not going to, this is not going to happen at the same time. So you don't normally just add these together. We're going to combine them in a how do I describe it? It's uncertainty propagation. So we're going to, one does they don't necessarily affect one another, but they occur at the same time. So why don't we do some examples? I might have to get some more paper. Let's see. These are all written on, so we gotta find some new paper. Got lots of paper. All right. So let's since we've been talking with the multimeter and everything, let's do a multimeter based example. Let's say multimeter can't, or this one can't measure power, right? But we do hopefully remember that power in an electrical circuit equals the current times the voltage. At least that's one way to calculate it. And I can measure current and voltage, well, that current and that voltage. And so I could measure these two separately and then use an equation to combine them together to calculate power. All right. So we would write down, we would have, once we solve this, the power would equal some nominal value. So we're going to use capital N. N is going to be the nominal value. And we'll put a subscript P because it's the nominal value of power. Plus or minus, we'll use a U here. U is going to be uncertainty. And we'll also put a subscript P on there. So that's what we're looking for, is we want to generate this value by measuring current and voltage. All right. So let's say that we found the data sheet for our multimeter, and it says that the voltage in the resistor, so I'll use a R, is equal to 100 volts plus or minus 2 volts. So this plus or minus 2 volts came from, there's a 2% error around the nominal value. There's different ways that sometimes error is presented in the data sheet for a tool or whatever you're measuring. Sometimes it's a percent of full scale, and sometimes it's a percent of the value. So this one would be a 2% error on the value, the way I've written it here. Or maybe it's a 2% of full scale. I just don't know the full scale of this thing. We would also need to measure the current in the resistor. Let's say that it's a large amount of current. We're just making up numbers. This isn't actually related to the strain gauge at all. 10 amps plus or minus 0.3 amps. And so these plus or minuses, we got them one of two ways. We either took this measurement, 1,000 times and did the statistics to figure out this number, but we probably didn't do that. Probably what we did is we looked at the data sheet and it told us that there's a 2% error associated with the value of voltage. And there's a 0.03 or whatever percent error associated with the value of current. And we just calculated these based on information that the manufacturer of the tool provided us. That's more than likely how we got these numbers. We probably didn't make 1,000 measurements and calculate these. All right. So first, the nominal power. That's pretty straightforward. The nominal power is just the nominal values, 100 volts at 10 amps. So let's see, where's my calculator? 100 times 10 is going to be 1,000. Well, let's put 100 volts times 10 amps, 1,000 watts. Now, that would be the nominal value. So that's this one. What we could do here, this is not the right way to do it, but this is how you would generate the worst case without having to do any complex calculations or anything. You could get in the ballpark with this number, but you would know that your actual uncertainty is a smaller amount than what we're about to do. So what we could do is we could take the worst case scenario for both. So in this case, we could generate the highest amount of power if we use our maximum voltage of 102 and our maximum current of 10.3. That would give us, well, I guess it's not nominal anymore. It's power, right? Power max equals 102 times 10.3, 1050.6 watts. And then we could do the opposite of that. We could do our minimum is 100 minus 2, so 98 volts. And our minimum current would be 10 minus 3, so 9.7 amps. And get our minimum power value, 98 times 9.7, 950.6 watts. And then we could take and figure out what the difference between those two is, right? So our nominal power, this is not the right way. This is the worst case scenario, but it's a quick and easy way. The maximum power plus the minimum power divided by 2. So 1050, so we're taking the average, 0.6 watts plus 950.6 watts divided by 2 is, let's see, 1050.6 plus 950.6 divided by 2, 1000.6. Which is, close to where we wanted it to be based on our nominal just 100 times 10 calculation. And the uncertainty would be if we took the basically the difference in these and divided by 2. So 1050, so we'll do a plus minus 1050 minus 950.6 and divide that. That's 100. There's 100 watts between there. Divide that by 2 and we have 50 watts. So this would tell us that under the worst possible conditions, where I actually either take and simultaneously measure the highest voltage and the highest current, or the lowest voltage and the lowest current, then I could have as bad as 50 watts. I could be off by as far as 50 watts from the nominal value. Again, this is not the way that we actually do uncertainty. This is just the way that you would go in and see what are you even dealing with. So this is a quick way. There's no complicated math in here. You just take the maximum values, use all of those in your equation, figure out what that is, and then take all the minimum values and use that in your equation. I guess you have to look at the equation and make sure. Sometimes it makes more sense to use a maximum value when you're trying to calculate the P min, like if it's in the denominator or something. So you do have to look at the equation. You don't automatically take all the maximums and all the minimums. You take the worst case in one direction and then the worst case in the other direction. This one, obviously, since we're just multiplying, we use the maximums. But if we had some division in there, we might have to mix and match maximums and minimums. Again, that's not actually the way to do this, though. This is just to get a rough ballpark. What we do know, though, is that when we calculate the real uncertainty, it should be less than this. So this is the worst case uncertainty, 50 plus or minus 50 watts. When we calculate uncertainty, we should get a number that's smaller than this. When we try to predict that you're never going to actually measure all of this at the worst scenario at once. At least you're probably not going to. 95, well, where'd our 95 go? Moved it. We're 95% sure we're not going to do the maximum things both at the same time. Or all at the same time. All right, so how do we do this? All right, so this is where it's not necessarily statistical, at least not outside of this. This is where the statistics are. They were back behind the scenes to generate this this tolerance in the first place. So we're going to assume we know the plus or minus on our individual measurements, the uncertainty in our individual measurements. We're going to assume we know that because we're using quality tools that we have data sheets for, or maybe we've used this tool and we actually have done thousands of measurements with it and figured out what the tolerance is on that tool. We do have to know that piece of information somehow. So either we're using tools that come with certifications that trace them back to the standards so that we know what their uncertainty is, or we've done it ourselves, and normally you're not going to do it yourself, but you could. All right, so this is the right way. We're going to set up an equation y. In our previous, y would just be the result, p, power. But we're using y as kind of a generic variable. And this result is a function of a lot of variables. We don't know x1, x2, a bunch of variables. So in our case that we just did, p is a function of I and v, right? So this is what we're writing here in generic terms, all right? And we can calculate a nominal value. So what we did is we just multiplied the nominal value of current times the nominal value of voltage, and we got the nominal value of power. So I guess we could write it this way. For a particular set of measurements, I can make this measurement many times, right? I could reattach the multimeter, I could turn it off and back on and make it a lot of times. But for a particular set K, all I'm going to write here is basically it's x1, but it's measured at the K instance. x2, that should be a 1, not a I. Measured at the K instance. See if I can make bigger commas here between them. Those aren't G's. So this is just a particular measurement. This is the general form of the nominal value. This is a particular measurement where I've gone in one time and measured all my variables. What I can do is use the Taylor series expansion. So I don't know if I know you've done that before in a math class. I don't know if you've used it in anything outside of math class or not. But what Taylor series do is they're really good at taking complex functions and approximating them with polynomials. So polynomials are generally easy to do things with. One of the things we're about to have to do is take partial derivatives, and it's pretty easy to take partial derivatives of polynomials. So we're going to take and create a Taylor series expansion of our instance here. So yk is equal to the true value. So the true value is kind of like the nominal value, but it's the actual value, the one around which we're going to center our uncertainty. And then I need to expand. So how you do Taylor series is you take first derivatives, add them to second derivatives, and add them to third derivatives, and on and on and on. We're going to eliminate all of the second, third, of the higher order terms and only use the first derivative. And they are partial derivatives. So I'm going to need the true value plus this first value for whatever variable 1 is. Maybe in here it was the current. So I only will have 2 in my actual equation when we do the power. But you could have many variables in an equation. So here's I measured the current in this instance K. I'm going to subtract off the true value of this, which again, I don't really know yet, but I have to write it down so we can do the next step. And then we're going to take a partial of the function with respect to this variable. Now, this part that we're spelling out step by step here, you don't do this part every time. We're doing this part to set up a generalized equation that we will use later. So this is just how we get to the point that we want to get to. And we would keep doing this. So I would do, if I had another variable, like in this one I have an I and a V, so current and voltage, I would do the next one, and it would look the same except I would have 2's in there, right? So plus x2, the K measurement of x2, minus the true value of x2, times, and this would be the partial with respect to x2. So basically, I would take the partial derivative of this equation with respect to I, and then respect to V. So this one's really simple, but that's no matter what the equation is, that's the idea of it. All right, so, and then I keep going. You know, if I have 3 or 4 variables, I keep adding. I just ran out of room on my paper, barely even got that on there. So, and there are, for the Taylor series expansion, I would do this multiple times. I would have the first order derivative and the second order derivative and the third order and so forth. And the more derivatives you take, the better your approximation that we're making here, the better that approximation fits the actual data. That's not always true, or at least it is always true within a range, a certain range. But right now we're just doing the first derivative. We're not doing any of the higher order terms. So there would be higher order terms if we were to write this out. We're just saying that those are so small we're not going to worry with them. And now what we can do is we can rearrange this thing in a convenient way for us, so that let's take our true value and put it over here. So this guy, and then I think we would leave this one more or less the same. I'm not going to rewrite it. Well, maybe I will, so that we're not all squished up over there. All right, so, and again, we're dropping off the higher order terms. All right, so all we did really is move this value over to here. So now we have the measurement minus the true value. So we have something that is starting to begin to look like uncertainty. In fact, we could make the statement that any value x, I, k, so it doesn't matter if it's the x1 or the x2 or the x3 or whatever, is equal to that value's true value. So it equals this guy plus u, which we had way over here. U is the uncertainty. So plus the uncertainty in that measurement. And so if we take this, I don't know if I want to write a bunch of these out, but if we take this idea where the true value is basically what we measured plus some uncertainty, or plus or minus some uncertainty, we don't know. Then if we take that idea and write it out into this equation, it'll look sort of like, and we'd have the same thing for this too, right? The true value plus some uncertainty in the calculated result. So basically we're taking yk, putting yk equals the y true value plus the uncertainty in y. So that is for this one minus the true value. And let's write out this one term here, and then we won't have room to write that one out. x1 true value plus the uncertainty in 1 for that measurement. So that's basically taking the xik, in this case we're using variable 1, so x1k, plugging in this for it, says the true value plus uncertainty. But then I need to subtract off x1 true, and then there's the partial f with respect to x1. What it does is, this is the point of it. Y true minus y true, x1 true minus x1 true. And it leaves me with the uncertainties. And that's what I'm trying to get at. The uncertainty in y at measurement instance k, so the time that I'm measuring it, equals the uncertainty in variable 1. Oh, I don't know why I keep writing that as I. Variable 1 at this time k. Eventually we'll drop the k's off, but they do make it the point that it is this measurement. I don't take different times to do this. Times the partial with respect to x1, whatever variable 1 is, so the current or the voltage or whatever it is I'm measuring, plus, and then we would do u2 in this measurement set, partial x2, so the voltage. I can take this equation and let's see if we can get them all on here and generalize it to this. Well, actually, yeah, let's generalize it to this. So the uncertainty in the result of measurement k equals, this is just a summation, the summation of all the individual uncertainties for this set of measurements times their partial derivative of the function, whatever the function is. In our case, it's the function is power equals current times voltage. And you take those partial derivatives with respect to whatever variable 1, variable 2, variable 3. The problem with this is that this is a summation where some of the uncertainties can be negative and some can be positive, because it's a plus or minus thing, and so sometimes you'll get negative numbers, sometimes you get positive numbers. And Kline and McClintock they came along and said that, well, we can use a RSS, so that's root sum square. So this is the square root, the summation, and square. So if we square this, or at least the uncertainty part of it, then we'll eliminate the fact that some of our negative uncertainties could cancel out our positive uncertainties. So if we square it, then that'll eliminate that, and it's a summation, so that's the summation. And then we need to take the square root of it because we squared all these things and they're too big now. So Kline and McClintock equation is this: uncertainty is equal in a result at some measurement k is the square root of the summation of all your variables from I equals 1 to n, the uncertainty in that variable, so in the uncertainty in the voltage or the uncertainty in the current or whatever it is, times the partial derivative of the function p equals I times v with respect to each one of those variables, I and v and whatever it is. But that is squared so that we can eliminate the idea that the negative uncertainty will cancel out the positive uncertainty and it'll just go to 0. This is what we'll actually do, and it looks really complicated. And it can be, depending on this function, right? Because you have to take these partial derivatives. So there are some times where you just have to do this with numerically, or Wolfram or MathCAD or something like that to actually do the partial derivatives. Our equation is power equals current times voltage, so we can do that with no other tools. So let's go back to where we were. Let's start a new page. Keep this one handy because we'll need it. But let's go back to where we were. We were power equals I times V, which is just a basic little equation that we learned 3 years ago, or maybe even longer, I don't know. And we had the voltage in our resistor was 100 volts plus or minus 2 volts. And so the plus or minus 2 came from some knowledge that we have about the tool that we use to measure the 100 volts. The current was 10 amps plus or minus 0.3 amps. And again, the plus or minus 0.3 came from knowledge about the tool. All right, so we start out the same. The nominal power equals the nominal voltage times the nominal current is 100 volts times 10 amps equals 1,000 watts. So start out with that. And that is, in our previous example, this is Y. So this value is the result, Y. All right. Now we need to do the uncertainty part. All right, so let's expand this guy. We only have two variables, so it won't be crazy. The uncertainty in our power is equal to the square root. So uncertainty in our power, Y is power. Well, I'm dropping off the K. We've only got one set of variables, one set of measurements, the 100 plus or minus 2 and the 10 plus or minus 0.3. So I'm not going to include the K's anymore. They're kind of just in the way. So it's square root of the summation, and we got to do this 2 times, once for the variable V and once for the variable I. All right, so for the variable V, we have the uncertainty in V, which is over here. No, here, V, times the partial derivative of our function, F, with respect to V. And we square this thing. And then we add, because it's a summation, so we have to do this for every variable that we have. In here, our variables were called x sub I. So x sub I here is V. In the next one, x sub I will be I, current. So we have the uncertainty in our current times the partial derivative of our function with respect to that current. And we square this. All right, so this one, the partial derivative, let's just go ahead and write them out. Partial derivative of our function is P equals I times V, right? So the partial derivative of F with respect to V is I. And the value for that would be the nominal. I guess I should put that it's the nominal value. When we go to plug I into our equation, to actually put a number in here, we're going to use 10 amps. So we'll put the nominal value for I. Partial function of our equation with respect to I is the nominal, you take the derivative of this thing with respect to I, it's just V. But it's going to be the nominal value of V. So the 100 volts. So if we plug these things in, so we've got in I is 10 amps, in V is 100 volts, uncertainty in V is 2 volts, and uncertainty in I is 0.3 amps, right? All right, so let's see. Uncertainty in power is the square root of the uncertainty in the voltage, 2 volts, times the partial derivative of F with respect to V, which is the nominal value of the current, 10 amps. And we square that term, plus the uncertainty in the current, which is 0.3 amps, times the partial derivative of the function with respect to I, which is the nominal value of the voltage, 100 volts. And we square that term. And you should be able to make sure that these units actually work out. So I have voltage times amps, amps times volts. So these units I actually can add together. If you ever come out and try to do this and the units don't add together correctly, then you've made a mistake, probably in calculating a partial derivative. Or one thing that is easy to make the mistake of is flipping these two. You're looking at V and you put a V in here, so you put 2 volts times 100 volts. You do something like that. So it's kind of little careless things when this goes wrong. So the math here, well, let's see. Where's my calculator? I've lost it. Here it is. So we have 2 times, whoops, hold on. All right, 2 times 10 squared. So I've got the square root of this one is 400. And this would be watts, right? Volts times amps would be watts. Although it's watts squared, I guess, because we have them squared. I usually don't put the units on there. I just did now. 0.3 times 100 squared, 900. And these would also be those watts squared. So 900 plus 400. And then we take the square root of that. And we get 36.06 watts. Now, if we go way back, if I still can find it, when we did this the first time with the wrong way to do it, where you just find the worst possible case for both extremes, what's the highest number we could calculate with our tolerances and what's the lowest number, uncertainties. And we had a 50 watt plus or minus uncertainty. When we do it the right way, it's tightened it up. It's 36 watts of uncertainty, which is generally better to have smaller uncertainties. And what we did here, what's behind the scenes is, well, it's this related back to, you know, something like this. We had to know the 2 and the 0.3. The one thing that I didn't really point out, I pointed out earlier, but is that this 0.2 or plus or minus 2 and this plus or minus 0.3, those both have to be at 95%, or they both have to be at 99.7%. You know, the uncertainty in these measurements have to be the same level of uncertainty. And typically it's going to be 95%. If it never says one way or the other, then it's almost certain that it's at 95%. Unless you're specifically told differently, the uncertainties are at 95%. So that's a simple example. There's two other examples on Moodle that they go in and do the same thing, but they do it in Python. I don't have time, I don't think, to do that today. We'll go through one of them. Yeah, we'll do one of them next time, because one of these examples shows how to do the derivatives in Python. And so that might be useful. If I were doing these problems, I really wouldn't do them in Python unless I was just trying to improve my coding skills. I would do them in MathCAD, which is going to do a better job of helping you track these partial derivatives and actually see them, versus Python is going to use a finite difference method that you may not really be familiar with yet. But in MathCAD or even Wolfram, you just can't code it then. It's going to look more like what you expect. Although this one, you don't need to do, you know, on an exam, you're going to have more like this, where the calculation of the partial derivative is pretty straightforward. Nothing really complicated. Okay, I think that is enough for today. What you need to be doing is, I do need to know what teams you're working on and your sensors. I've gotten a lot, maybe 2/3 of everybody has given me something. And I haven't looked at the stuff that's turned in on Moodle yet, so maybe there's more in there. A couple of things about that. So the idea on the bigger project is that you have a group of people, up to 4. It could be 1, 2, 3, or 4, but you have up to 4 people. All the people in that group have the same sensor, and you record the same type of data for 3 days straight. So I don't know, maybe you all get a sensor, the photoresistor, and you put this thing in your refrigerator, and you track when the refrigerator's door is open for 3 days straight. And then it's 3 different refrigerators, or however many people in your group, and then you can compare and contrast that data set later on. Something like that, where you all have the same sensor in your group, and you're all measuring the same type of data, and then we're compiling it later to make any judgments that we can make about what the data was telling us. Let's see. You do need to build this Wheatstone bridge. And the goal here is and you don't have to have these particular types of wires or anything. You can just use regular wires. They don't have to be the fancy ones with the little ends on them. The goal here is to balance your bridge so that it reads pretty close to 0 when it's just sitting static, but then you can measure the voltage across I don't even know where that sheet's at anymore, but across the bridge. And as you flex the beam, you should get a tiny change in voltage. And then next week, we will amplify that tiny change to get a measurable change, something our Arduino can actually measure in voltage. I think that's going to cover everything that we're at today. I will see you next week. All right.